a normal projective variety with mild singularities. In general, for example, the Q factorial and the KRT singularities. And we also consider a finite surjective endomorphism F. We also frequently use the following notation in case of any confusion. First, the n upper 1x denoted by the finite dimensional real vector space of R Cartier divisors modular numerical equivalence. You can also regard it as the Néron-Savary group tensor with R. And its dimension is denoted by rho x, the Picard number of x. We also consider the cones of Neff Cartier divisors, meaning that the Cartier divisors with the R Cartier divisors with intersection non-negative for any curve, and also the pseudo-effective cone of which is the closure of the effect divisors. We also consider the dual space of n upper 1, which we denote by n lower 1x, which is the space of 1 cycles, also modular numerical equivalence. And it's pseudo-effective 1 cycle cone. Okay. Let's briefly recall the mini-model program. If the canonical divisor is Neff, then we do nothing, we stop. And if the canonical divisor is not Neff, then any kx negative extremal ray in the pseudo-effective 1 cycle cone is contractible. Precisely, we recall the cone theorem. So there is an algebraic fibration pi x to y such that the extremal ray is generated by some rational curve C, which is contracted, and the curve C is contracted to a point if and only if its class lies in the extremal ray. Third, there is an exact sequence. Here it is a short exact sequence. The first is by pullback, and the second is by intersection with the contracting curve. By tensoring with R, we have the exact sequence. In particular, the Picard number of y is equal to the Picard number of x minus 1. So
let me interrupt you. Do you assume any condition on singularity of x?
Yeah, mild singularity. Okay. Q factorial KRT. Yeah.
Okay, good.
Yeah. And then, so in particular, we can view the n upper 1 y as a hyperplane of n upper 1 x via the pullback action. There are three types of the contraction: the divisorial contraction, flipping contraction, final contraction. For the divisorial contraction and final contraction, y preserve the mild singularities, especially for the Q factorial singularities. However, for the flipping contraction, the image y must not be Q factorial, even though Q constant. So we need the flip to save the singularities. So here it is the diagram. And the rational map here, birational map here is called the flip. But the disadvantage is that the Picard number will increase. So the Picard number of x and the Picard number of x plus are the same. So this comes up to a natural hard conjecture about the termination of flips, which is known only in dimensional 3. However, with the result of BCHM, with the special termination, we can find a very special finite sequence of MMP involving with the three types of contraction, two types of the contraction, divisorial, final, and the flips, such as the end product XR has a pseudo-effective canonical divisor. Here we don't require the end product has the left divisor. Okay. Okay, now we come to the part of the equivariant MMP. So the definition is simple. So given any finite sequence of MMP starting from X, and the equate X with an morphism F, we say it is F equivariant if the following diagram commutes after iteration. So here our first endomorphism is F1, but F1 is the some iterate of F. Here is the direct criteria for the possibility of EMMP. Consider the induced invertible linear map while the push forward action. Sorry, here is the n lower one. Sorry, here is a typo. The n lower 1x to n lower 1x. Then after iteration, the first step is F equivariant if and only if the extremal ray, here R is the extremal ray contracted, is preserved by the push forward action. And this if and only if result can be easily get from the repeated lemma and the projection formula. Okay. So now let's state the known result for the equivariancy. Any question? Okay, so there are three types of possible equivariancy. First is for the Moore dream space, like the variety of phenotype. And Nakayama proved the equivariancy for the surfaces case and non-isomorphic endomorphism. That means that the degree of F is greater than 1. In general, in higher dimensional, such equivariancy may not hold. But John and I show that if X admits a polarized or anti-amplified endomorphism, then any endomorphism, any suggested endomorphism of X, you can run the EMMP. So here is the quick definition. I guess Shibata already introduced the definition of Q polarized. So it is G pullback H linear equivalent to QH for some ample divisor H and integer Q greater than 1. And G is anti-amplified if G pullback H minus H is ample for some ample divisor. So it amplified this ample divisor. Here is a very useful criteria. So first, to say G is Q polarized, then we can show that it is Q polarized if and only if the pullback action on N1X has Jordan canonical form, a diagonal matrix with all the eigenvalues having modulus equal to Q. One direction is shown by cell, and we show another direction. And if G is anti-amplified, then you can say it is anti-amplified if and only if the pullback action on N1X has all eigenvalues greater than 1. So you see the anti-amplified endomorphism is very natural. Okay. Sorry. Okay, I briefly explained the idea of the proof of the equivariancy. So the key point is to show the finiteness of the contractible extremal rays. Because the pullback or push forward action on this rays, it permutes the contractible extremal rays. So if it is finiteness, so then after iteration, it will preserve all the contractible extremal rays. For the first case situation, when X is a Moore dream space, then any MMP involves only Moore dream spaces. So we only need to show the equivariancy for the first step. Note that for the definition of the Moore dream space, we only need that the pseudo effective one cycle cone is the rational polyhedron. So it means that there are only finitely many extremal rays. So this case is simple. For the surface case, Nakayama indeed proved that there are only finitely many negative curves. And note that contractible curves are always negative by negativity lemma. And for the third case, we first make use of the result by Dean and Siboni, showing that there are only finitely many totally periodic subvarieties, meaning that the pre-image of Z equal to Z after iteration. We also call it a G inverse periodic. And then we show that contraction locus of each contractible extremal ray is G inverse periodic. And for each contraction locus, it can be shared by only finitely many contractible extreme arrays. So these two arguments imply that there are only finitely many contractible extreme arrays. And so we can run MMP for this kind for all the endomorphisms if X admits polarized or inter-amplified endomorphism. Okay. As we have seen that if we use the special termination, although we have only finite many sequence, although we have only finite many steps, but our end product has only pseudo-effective canonical divisor. However, with our dynamic assumption, it is already good enough because this theorem tells us that if X is a KRT projective variety without Q factorial assumption, admitting an inter-amplified endomorphism, and suppose the canonical divisor is pseudo-effective, then X is Q abelian, meaning that it is a quasi-état quotient of some abelian variety. This is a combinatorial work by Grab, Pecos, Peter Nair, Nakayama, and Zhang, and I generate it through the inter-amplified case. The main idea is to make use of the ramification divisor formula. So here it is the ramification divisor formula, and the RG is the ramification divisor, which is effective. If KX is pseudo-effective, then we can show that the ramification divisor cannot be together with the pseudo-effective of KX and the effective of RG. RG can only be trivial, so RG equal to 0. So by removing this RG, we see that KX equal to G pulled by KX. So in particular, KX, you find an eigenvector, which is KX with eigenvalue 1. However, we know that G is inter-amplified. As we see, G has all, the pullback has all the eigenvalues modulus greater than 1. So this is not possible unless KX itself is trivial. So it is not an eigenvector. The second step, a little bit technical. I simply give the main result. So by taking the Galois closure of the case iterator of G for sufficiently large K, we eventually get a quasi-état cover pi, such that this cover is smooth, and the first and the second Chern class vanishes. And then we apply the Yau's result. There is a quasi-état cover for X prime, and the cover A is an abelian variety. So together, we say we compose tau and pi, so we see X has a quasi-état cover A. But however, this cover is not constructed equivariantly. So we need to choose carefully, very carefully, a good cover, so-called Albanese closure. And this result is done by Nakayama and Zhang, and the importative characteristic done by Cassini, Zhang, and I. So it says that we can choose a good cover, such as a diagram commutes for any surjective endomorphism f of X. And with this proposition, we have the following corollary. So let XR be the end product of our inter-amplified EMMP. We consider the composition from the very beginning to the end. In general, it is a rational map. However, with the proposition, we can show that it is a morphism. It's a well-defined morphism and also equidimensional, meaning that all the fibers have the same dimension. And indeed, you can also show that all the fibers are irreducible. And the second, if the algebraic fundamental group of the smooth locus of X is finite, for example, X is smooth rationally connected. In this case, it is simply connected. Then we can show that the end product is a point. Here, the idea is quite simple. Okay, we prove the corollary using the proposition. First, note that the inter-amplified endomorphism of an abelian variety has no totally periodic subvariety proper in properly in this abelian variety. Because any endomorphism, any suggested endomorphism of abelian variety is étale, has no ramification. However, for inter-amplified endomorphism, any totally periodic subvariety must create ramification. So this comes to a contradiction. So, and secondly, we note that the special fibers are totally invariant. Here are special, you can take special fibers like the higher dimensional fibers that you can see, or non-reducible, or reducible fibers. And these fibers are the image of these fibers are totally invariant. So these two arguments implies that it must be well defined, and all the fibers have the same dimension. For the second, if the end product is not a point, and we see it is a positive dimensional Q abelian variety, so it admits an arbitrary large degree cos eta cover. And hence, by the base change, by taking the base change, and by 1, because it is equidimensional, the base change induces an arbitrary large degree cos eta cover, which implies that the algebra fundamental group here is not finite. Okay. Okay, so now we come back to look at the pullback action. Why the step-by-step EMMP? We can show that the pullback action on n upper 1x is diagonalizable if and only if so is the pullback action on the end product. The idea is simply making use of the following commutative diagram, and we only need to consider the step when it is a divisorial or final contraction. Anyway, we have the following diagram, and it is a hyperplane of this. The first is the hyperplane of the middle one. For the divisorial contraction, you let E be the exceptional divisor of pi, and then you see that by the equivariancy, we see that you pull back E, it equals to some multiple of E. So naturally, E is an eigenvector. So this is simple. However, for the final contraction, we don't know how to find the eigenvector. But we can only show the existence, and we know nothing about the property of this eigenvector. And the proof is by using multilinear algebra and intersection argument. Okay, so this is roughly the introduction to the EMMP. Do you have any question? Okay, so let's quickly okay, now let's come to the third part, the application. Okay, for this part, I'll only list the results without detailed explanation. We focus. I recommend you to focus on the various assumptions on the results for the purpose of the last section. Okay. So the first application is about the question on Calabi-Yau, the Calabi-Yau type and phenotype problem. Recall that X is of a Calabi-Yau type. If there is a pair which is the log canonical, and Kx plus delta is numerically trivial. And indeed, by Gonyos abundance result, you can replace this by Q linear equivalence. And the X is a phenotype if the pair has KRT singularities, and minus K plus delta is ample. Brustad and Gonyo make the following conjecture. So they boldly asserts that a normal projective variety without any singularity assumption, that if it admits a polarized or inter-amplified anamorphism, then it must be of Calabi-Yau type. They themselves solve the surface case. And for higher dimensional, it is much complicated. However, recently Yoshikawa proved the following: a smooth rationally connected projective variety is a phenotype if it admits an inter-amplified anamorphism. So here, smoothness is very important. If you remove this assumption, it is not correct. There are counterexamples. But however, we want to remark that Yoshikawa constructed a very special log MMP, not our pure MMP. This MMP is chosen by carefully concerning the coefficients of the ramification divisor. John and I also have another approach, but not the EMMP approach. We show that if X is a normal projective variety, here also without any singularity assumption, but we need the so-called Q-Gorenstein assumption, Q Cartier Kx. If X admits an inter-amplified anamorphism, we show that minus Kx is Q effective, meaning that some multiple of minus Kx is linearly equivalent to some effective Cartier divisor delta. So you see that we constructed a log pair X delta over M, and Kx plus delta over M is trivial. But however, we don't know how to move this effective divisor to such that the pair, making this pair have some good singularity, like log canonical. One possible way is to using the pre-image of delta or F or the image of delta, but still there are some problems here. Okay. A second application is a bit more rigid. The first conjecture probably proposed by Fakhruddin. He said that a smooth rationally connected projective variety is toric if and only if it admits an inter-amplified anamorphism. So note that here it is if and only if. This conjecture is generalized an early conjecture about the following. So a smooth Fano variety X. So Fano variety must be rationally connected. A smooth Fano variety and also of pickup number 1 is nothing but projective space if and only if it admits a non-isomorphic. Since it is pickup number 1, so if non-isomorphic, it is automatically polarized anamorphism. It is also if and only if. And you see that this conjecture implies this. First, they imply the second conjecture because the toric, smooth toric pickup number 1 must be P. One direction is simple. Because every toric variety admits the polarized anamorphism, which induced from the power map on the algebraic torus. The second conjecture has been verified for the following following situations. Especially, it is now known for the dimensional 3, and these two implies that if it admits a non-isomorphic anamorphism, it cannot be a hypersurface of a projective space. Okay, and Huang and Work also show that if it admits, it is not possible for variety admitting rational curve with trivial normal bundle. Okay, now we come to the first conjecture. The surface case has been done by Nakayama. A smooth rational or rational connected surface is toric if and only if it admits a non-isomorphic anamorphism. Here, non-isomorphic is not strange because for the smooth surface case, if it admits a non-isomorphic anamorphism, which is not polarized, then it has to be P1 cross P1. And we can see it in the dimensional 3 situation. John and I show that in dimensional 3, if X is a smooth Fano threefold, then X is toric if and only if X admits an inter-amplified anamorphism. And if it only admits a non-isomorphic anamorphism, which is not anti-amplified, then it splits. It is even better. So you see X split as some diapedal surface and a rational curve. Okay, all these approaches are using equivariant minimum model program. And the third another interesting situation done by Zhong and I, we show that if it is not polarized, okay, and we look at the eigenvalues, if they are at least n different eigenvalues greater than 1, then it must split. So if X is a smooth rational connected variety, it is totally splits at the P1 cross P1 cross P1 nth product. Okay, if it admits such anamorphism with n different eigenvalues here, real eigenvalues greater than 1. So this definition implies automatically anamorphism is anti-amplified, such that we can run the EMMP for X. Yeah. Okay. Okay. So I will mention one more conjecture towards the axiomatic dynamics. I guess Shibata already mentioned this just now. So I quickly review it. Okay. So the Kawaguchi-Seelman conjecture asks whether for a suggested anamorphism of a projective variety defined over a number field or Q bar, then the axiomatic degree of X equal to the first dynamic degree. Here he used the D1F. Okay. And with any point such that the forward orbit is Zariski dense. Okay. Here are the quick definition. Here the definition is a little bit different from his. Because our F is a well-defined anamorphism, so I simply define this as the spectral radius of the pullback action on N1X, which is the maximal of the modulus of the eigenvalues, because we are already familiar with this. The arithmetic degree function is defined by the wave height function associated with some ample divisor in this form. Okay, we don't care about the arithmetic degree here. Okay, I will mention the induction later. So Kawaguchi-Seelman themselves use the linear algebra proof that the alpha fx equals to either 1 or the modulus of some eigenvalues of the pullback action. So in particular, we see that the polarized anamorphism have modulus equal to Q. So this part is always Q. So we only need to exclude the one case, and eventually he can show that it is true for polarized anamorphism. There are some other approach given some partial result for KSC. This one is important for us, abelian varieties. And Lejeune and Satriano proved the hyperkähler varieties and smooth threefold with a smooth project threefold with codal dimension 0 and degree F greater than 1. Okay. So in general, there is a good induction method. So we focus on this, and we don't care about the arithmetic degree now. So if the anamorphism is not polarized, we try. The key is to find an equivariant fibration such that the dimension decrease and the dynamic degree preserved. If so, the Kawaguchi-Seelman conjecture for F, we can reduce it to the Kawaguchi-Seelman conjecture for F restriction on 1. So now you see this, by this induction, this arithmetic problem is turned into totally purely a geometric problem, dynamic geometric problem. Yeah. Here are some EMMP approach. So John and I showed that they hold for any projective surface without any singularities. And Matsuzawa and Yoshikawa showed that it holds for smooth rationally connected case admitting an anti-amplified anamorphism. And Matsuzawa, Shibata, John and I showed it for smooth projective threefold admitting an anti-amplified anamorphism. Indeed, we can weaken this assumption to Q factorial terminal. Yeah. Because the birational MMP preserves the terminal singularities. Okay, so this is the end of the third part about the application. Any question? So now later we'll move to the main part of this talk. Okay. So you see, so we have seen the various assumption or restriction on our conditions. First is about singularities. We want to free ourselves from these singularity settings first. Here are some known results. I just skipped the reason why for the surface case we can run EMMP, because for normal it is not easy for you to run normal MMP for normal projective surface. However, we'll show that if it admits a non-isomorphic anamorphism, it automatically admits a log canonical singularity. And with this, we can run MMP. And in higher dimensional case, Brostad and Hurin prove that a normal projective variety with Q-Cartier canonical divisor has log canonical singularity if it admits an anti-amplified anamorphism. But this definition is bad. Okay, but without this condition, Yoshikawa proved that it has at worst the valuative log canonical singularities. This is a little bit bad than. This is worse than the log canonical singularities, so we don't know how to make use of this. But luckily, but a good result, he applied the result to show that the end product is good. Okay, so if X has a cos eta anti-amplified anamorphism, then it has log canonical singularities. And moreover, the canonical divisor is nothing but a torsion divisor. So you see, the Q Gorenstein, although already very big, but for the dynamic purpose, it is still not good enough because it cannot be preserved by MMP. So our wish is it possible to find some effective Q divisor delta such that the pair is log canonical. As we see the case 4, the cos eta is equivalent to the canonical divisor being pseudo-effective. So we asked whether the canonical divisor, if the canonical divisor is not pseudo-effective, then can we further require that to make the delta as small as possible, such that it is still not pseudo-effective, such that we can run the log MMP. So far, this kind of log MMP is still not established well yet. Okay, so this remains to be a very difficult problem. Okay. Okay, now we come to the second gap. Okay, about I call it saving the dynamic degree. The first dynamic degree is an important birational invariant, but it can decrease via a final contraction. Here, I mean, F is an anamorphism acting on X and G, and descent to an anamorphism G on Y, and pi is a final contraction of some extreme array. If the dynamic degree delta F equals to delta G, then we save the dynamic degree, and then we say it is good. For example, we can apply to show the KSC for F by reducing to show the KSC for G, and then we show by induction. So from now on, we assume that the dynamical degree decrease, and our assumption is still mild singular X with an anti-amplified anamorphism. Okay, so this is our current setup. Okay. So what can we do now? How do we save the dynamic degree? First, we see that since delta F is greater than delta G, and the Néron-Serre of Y is a hyperplane of Néron-Serre of X, so delta F is the only eigenvector, the only eigenvalue with modulus equals to delta F. So this is a unique, so delta F is a unique eigenvalue, even counting multiplicity. So therefore, we can find an eigenvector. Okay, so D is an eigenvector, and with eigenvalue Q, and Q equals delta F. And now you can see delta F is an integer. And you can find, and since the eigenvector is not coming from Y, so it is either pi ample or pi anti-ample. You can, if it is an anti-ample, you just replace D by minus D. And as such, by the uniqueness, you can also show that such D lies in an extremal ray of the Neff cone, and also the pseudo-effective cone. This is important proposition. Okay, this is our first step. Find an eigenvector. And recall that we know that the minus kx is effective and pi ample because we are contracting k negative curve, so it is pi ample. And we define B equals to D plus A kx such that the B is pi trivial. Here A is then chosen to be a positive rational number. Okay, there are two situations. First, if B is not pseudo-effective, then this is an open condition, non-pseudo-effective. So we can B over A plus some very small ample divisor. It is still not pseudo-effective, and we let A equal to H plus D over A. Note that H is ample, and our D is Neff here. Our D is Neff. So A is still ample. And consider Kx plus A, which equals to, you see, it is the B over A plus H, and it is not pseudo-effective. And moreover, if you let C be the curve contracted by pi, you see that Kx plus A intersected with C equals to B over A intersected with C plus H intersected with C. This part, note that B is pi trivial, so this part is trivial. The H is ample, so this is positive. So together it is positive. So what can we, so then we have, the let A equals to this, and we run K plus A MMP. This is also K MMP indeed, but we choose a very special one. So K plus A MMP with scaling of A. And since we see that K plus A intersect with general fiber of pi is positive, so the general fiber of pi is never contracted during this new MMP. And this new MMP looks like this. So we have X, and after several finite steps of birational MMP, we arrive at X prime. And we have, since it is not pseudo, K plus A is not pseudo effective, so we have a final contraction to Y prime. And F descends to a surjective endomorphism G prime. And note that since the fiber of pi is not contracted, so it is preserved in Y prime. So in particular, you can see that the dynamic degree of G prime equals to the dynamic degree of F by the uniqueness of delta F. So we save the dynamic degree in this situation. Any question? Okay, let's look at the counter case. If B is pseudo-effective, we look at, we rearrange this equation. So we say D equals to B plus A minus KX. So note that this one is A is a positive minus, so this one is pseudo-effective. B is pseudo-effective by this assumption. And D is extremal in pseudo-effective cone. So extremal decomposed as two pseudo-effective dividers, meaning that it can only be B, D, KX parallel to each other. So in particular, we use this F pullback D equal QD. So we have pullback minus K equals Q minus K. Since the minus K is effective, so we still have two situations. Okay. So first is the Ithaka dimension of minus K is positive. In this case, we take the Ithaka vibration of minus K and replace carefully the image of the Ithaka vibration by a good model, variational model, which we call the Chow reduction, such that we have the following dominant rational map X to Z, and F descends equivariantly to a well-defined anamorphism, suggested anamorphism of Z, denoted by H, such that the dimension of Z is nothing but the Ithaka dimension of minus K and less than dimension X. And we can further show that H is delta F polarized. Is delta F equals to Q here. So here the inequality, because the Ithaka vibration is at most the dimension X. If they are the same, meaning that the minus K is a big divisor. So we see this, but minus K is also an eigenvector. So a big eigenvector implies F must be Q polarized. But as we see that the Q polarized, meaning that all the eigenvalues have the same modulus Q. So it is not possible for you to have another eigenvalue, delta G, not equal to delta F. So this is the contradiction. So we have the strict inequality here. And in this case, we save the dynamic degree because we descend to F to H, and Z is a positive dimensional. Or here, Z is the positive dimensional because the Ithaka is greater than 0. So we are left with the case when, so here, we are left with the case when Ithaka dimensional equals to 0. The minus Kx, then we can show that the minus Kx is Q linearly equivalent to some not only effective, but also a prime divisor. And moreover, we can explicitly write the ramification divisor as delta F minus 1 D. And since this is 0, meaning that D is not movable. So you can see that D is totally invariant. This implies that outside D, F is quasi eta. So no ramification divisor outside D. Okay, so let me summarize the left case, and I call it a case TR, meaning the totally invariant ramification. Here are our setup. The first 3 lines are our setup. The second line is about the Ithaka dimension of minus K, not movable, and NAF extremal. The third and the fourth, meaning that it has a totally invariant ramification. Okay. So we see that this case TR has many restraints. So a natural question is, can this case happen? So far, we can work out the two lower relative dimensional cases. So first, John and I can show that if the relative dimensional, so from this means that it is from an n-fold contracted to an n-1 fold. So the relative dimension is 1. So if in this case, it never occur. It never occur. And Matsuzawa, Shibata, John, and I showed further that the relative dimensional 2 cases will not occur, but will require further assumption on the singularities, the terminal singularities. This is not good, but also not bad, because for bidirectional MMP, terminal singularities can be preserved. So So these two combined can show that this one is, we can show the surface case for the KSC, and this one is for the terminal Q factorial threefold for the threefold case. Yeah. Here is an interesting example proposed by Matsuzawa and Yoshikawa. They consider the ruled surface over an elliptic curve defined by a decomposable vector-vector bundle. Here, L is a numerically trivial line bundle, but non-torsion. They constructed an NT-amplified anamorphism such that all the conditions of KSTR are satisfied, except here, the dynamic degree is preserved. So delta F equals delta F restriction on 1. And the third, although D is a prime divisor, and indeed D is a pi section, but the eigenvalue equals to Q, while Q equals to square root of delta F. Okay, so we see that the assumption about the dynamic degree delta F greater than delta Fy is important. Okay, in the end, I'll briefly talk about the idea of the proof. For the first case, we let F isomorphic to rational curve be the general fiber of pi. Then by the adjunction, we see that D intersect with the general fiber equals to 2. And we know that D must cover Y. And we can further show that D is also a double cover of Y because D intersects with F equals to 2. Then we take the base change of D over Y. We get pi prime x prime to D and a double cover x prime to x. Consider the pre-image D prime equals to P inverse D. Note that the base change, because we have the anamorphism on D, so the base change also equivariant. So the pre-image D prime, so the P is equivariant, so the pre-image is totally invariant. But now it has two irreducible components, while the diagonal embedding, here D cross Y, D is nothing but P inverse D. And the map is sending small d to D to DD. And this is the larger, so you can see this as this is not isomorphic. So you see this one contains two components. And we will show that the base change, after base change, x prime over D is still a final contraction, and also satisfying the TRR assumption. But now the situation is a little bit different because our D prime is not irreducible, meaning that the Ithaka dimension of minus k x prime is not 0. So we get a contradiction. Okay. In the relative dimensional 2 case, it is much more complicated, and our proof is a little bit technical. First, we show that D is not smooth in codimension 1. And then we do the base change, and do the base change of singular 1 dy. Okay, here D is not smooth in codimension 1, so we can consider it's a singular locus of D, and it's a divisorial part. And we can show that this part is totally invariant, and we can show this is the cover of Y. And then we by the base change, by the similar argument, we can philosophically we can show that we can get some non-irreducible part, and we get a contradiction. But the difficulty remains on showing that it is a final contraction. It is the conclusion of being final contraction is not satisfied. We cannot show it. So this part need to consider more about the singularities of x prime. Okay.
So let me interrupt you. For the part one, the idea, I forgot, is double cover, the base change is quasi-étal or not?
Yeah, quasi-étal.
So the anti-Ithaka dimension preserved.
Yeah.
Okay. Okay. Thanks.
Indeed, the here the KSTR is equivalent with removing this assumption in prime divisor. Okay. There are short version. There is a short version of KSTR. Many assumptions indeed implied by the others. Okay. The key is this one, and this one.
Okay.
Okay, and this one. Yeah, the prime is not very important. Okay. But if it is not prime, you get a contradiction always. Okay. So I think I finished here. Thank you.
Oh, you finished?
yeah, finished. I think it's okay, right? 7 or 8 minutes left. Yeah.
Quite tense. Yeah. Yeah. Any question and comments, please? So the Kawaguchi-Silverman conjecture, if you can say this TIR case, maybe show the TIR. If you can say the TIR case does not happen, then you can say Kawaguchi-Silverman conjecture is true, right?
No. But with assumption here, X admitting and inter-amplifier. For this kind of varieties, yeah, only for this kind of variety.
So you just need one inter-amplifier, then you can say all the other amplify KSC, right?
Yeah.
Any other question or comments?
So if you have polarized endomorphism, do you expect that after some final iteration, the pullback acts as scalar multiplication on the neuron several space?
No, this is not true. There are counterexamples, but I think maybe you can construct it easily from the product of every curves. So you can only show it is diagonalizable, and all the diagonal entries are of modulus Q. But you cannot say after taking power, they have after taking power they are all the integers. This is a good exercise. If for all the algebra integers matrix, if the diagonal have modulus 1, then you can show after taking power by Koronaka's result, all the entries equals to 1. This is okay. But if all the entries are of modulus Q, and it is suppose it is similar to an integral matrix, suppose, then but you cannot say after taking power all the entries equals to Q to the power of n. So there are the counterexamples. Yeah.
Good. Thank you very much.
Okay.
So the smoothness is also important in the result of Yoshikawa and Matsuzawa, right?
Almost, yeah. But they can also they cannot reduce to Q factorial. They cannot reduce to Q factorial terminal. But if you want, maybe I'm not very sure. Maybe you can remove this condition, smooth condition, by the algebraic fundamental group being finite. So meaning that EMMP end up with a point, then maybe it is okay.
Yeah.
But I'm not so sure.
Any more questions? If not, let's thank the speaker. Yeah.
Okay, thank you very much.
Yeah. Okay, so thanks for the two speakers. Maybe we see next time. Yeah. Okay.
Oh, you are. It's 5 o'clock there. Yeah.
It's 5:11.
Oh yeah, I'm 6 o'clock. Yeah, I need to go to dinner. Yeah.
Thanks to the audience.
Okay, thank you very much. Okay.
For the next time, for 2 weeks from now, the talk will be in the morning.
In the morning. Oh, okay.
Yeah.
Okay.
for next time.